All right, so it's 8:30 and we're getting started, and we're asking for people who are watching remotely to let us know if you can hear us well, or if you can make the camera focus elsewhere and so on. I wanted to thank you all for being here. It's an exciting event of the year when we have to present the final projects of our interns. It's the fifth time we do that, so it's very important for us to be completing this cycle with a lot of presentations. And I wanted to briefly talk about the iDASH project in general in biomedical informatics, because we work in different areas that all tie together according to the circle. And you will see projects at each one of those areas today. And iDASH in general was here to provide shared access to data and computation. So that was our goal in a privacy preserving manner. And the second bullet tells it all about this internship is to train the next generation of biomedical data scientists, provide innovative software structure platforms. And then you will see a lot of algorithms, tools, and other studies that are related to biomedical informatics. Some of our projects are run by ourselves in collaboration with other universities. They're presented here, their titles. Many of these are wrapped up this year. And the themes of privacy and the themes of genomics in natural language processing, you will see them repeat across some of the projects. So it's important to know that all of these presentations are part of a larger context. One of the projects that we are also, we just finished recruitment, is informed consent for clinical data use for research, IPR. And this is a project that came out of our understanding that no matter how we want to protect privacy is something very personal. And if people can select their own settings for privacy, that's something we would like to offer. And we're doing here in a pilot project at UCSD in which the patients can select what they want to share, and who they want to share those particular data categories with. So this is an exciting project, as well as the technology for doing distributed computing that will show up in some of the projects today. And that's our predictive modeling, but in a way that doesn't have to necessarily share the individual level data. You share access to that data to an algorithm. So an algorithm can go there, compute the data, but you don't need to move the data outside of the institution. So you see some projects today related to this distributed computing and privacy protection. This slide is also of what we envision as a data sharing center, or an iDASH commons, as we spoke, with some indexing that has to occur. This is a relatively new project that we have started less than a year ago. And it's about data being there, but you being able to know it's there, discovering it and using it. So we had focused on different types of models for data sharing. The traditional one you all know and use all the time, which is downloading data from a central facility. But the other two models are less developed, or had been less developed for biomedical data until very recently. One of them is to compute in the cloud, and in our case it's private cloud with human subjects protection. The other way is to do this distributed computation, as I said, so that you send computation and everyone collaborates without having to move the data around, which is particularly important because data are becoming very big and we don't want to be transmitted and around. And on the red font here, you see some of the techniques that were used in the course of iDASH for each one of those models of computation. And you will see some examples today as well. So iDASH has a tradition in this internship. It started in 2011 with 16 interns in several institutions around the country. And recently we have, as in the current year, international participation as well. Had I known we would present this slide, we would have recruited 16 interns for 2015. So it was a mistake on our part. But it's been very successful. And one thing that I wanted to let you all know is some of the outcomes of our interns. So this is the very first group picture. We'll take another group picture today, as it is traditional, of our iDASH internship in 2011, the very first. So some of the outcomes of the folks we have tracked, and there are others we have not tracked, so it can be equally impressive outcomes and positioning of prior interns are shown here. Some were postdocs at the time, like Mike and Dutton, who was organizing the internship, and are now assistant professors at different universities. Shuang is also co-organizer of this symposium, was an intern here in 2011, a postdoc until this year, and soon to be assistant professor at UCSD. So we're very proud of our prior interns, and we can see yourselves in those positions very soon. We have also an NLM, National Library of Medicine, training grant that started in 2012. It has 9 predoctoral and 6 postdoctoral slots, with also 3 short-term trainees per year. And we have, in the course of some years, those trainees came during the year, and some years they came together with the iDASH interns. So it's also a very important part of our training program. And I show some of the other PhDs and postdocs who were funded by the iDASH project, and the current ones and the total that we have there. So short-term trainees from iDASH, there were 63 total, with some of them here, some of them we tracked from the earlier days, but we will be tracking, and we're very excited about the outcomes. So this was pictures from last year, and I got this yesterday from Xiaochen, and I said, well, maybe you're not paying the interns. Well, why not? Because they were all buckets. But this was strawberry baking, wasn't it? Something much better than what you would tell from the picture. And we like to do social events, and hope we did some this year. Took some pictures. We did our traditional picture yesterday, last year as well, and we'll take one today. These are our interns from this year, so we're very proud, very happy to have you here. It was a very tight selection process, and we were the ones who were selected for a good reason. You come from several universities around the country, one from Brazil as well. 2 undergraduate students, and most of the others are graduate students, different years. So it's interesting because you won't tell from the presentations who is who. The presentations are all very nice. We have rehearsed them, and it's very exciting to have this diversity of institutions represented this year in iDASH. So I made a few modifications to the agenda just so that we have a little bit more time. We will have just 10 minutes for presentations. So if you could do 9 minutes plus one of discussion and questions, that would be fine. If you do the 10 minutes, we can accumulate questions towards the end. We will have a break, and for those watching remotely from 9:45 Pacific to 10, we'll have a break, take a picture, come back, and then start again at 10, and conclude around 11:15. Shelton will do the final remarks, and then we have a network lunch across the street. our own building, second floor. So it's going to be an exciting event. So with that, I would like to start introducing our first presenter, who is Danielle Garcia Ulloa from Emory University on recommender systems for biometric. So please welcome Danielle.
Good morning, and thank you all for coming. My name is Daniel Garcia Ulloa, and I'll talk briefly about the project that we have been working on during the summer. The name of it is Recommender Systems for Biomedical Datasets. So a little bit about ourselves. The project mentor is Shaoshan Jiang, and I am a PhD student in computer science at Emory University in Atlanta. Now a brief outline of the presentation. We're going to be talking a little bit about motivation and the background behind the recommender system, and then the recommender system itself, and two different approaches that we're taking, and finally some future work. So suppose that there is a published paper, and in biomedical sciences or in any science, and this paper has different references. So it's referring to these three papers in this example. And these references as well as are also referencing other papers. And in the same way, there are papers that are citing this published paper. So all of this creates a network of papers. On the other hand, we have the authors who created this paper, the authors who wrote this paper. And well, in this case, we have an author that also was a participant in one of the papers that is citing the paper. And other authors that are citing the reference papers and also the citations. So this also creates a network of authors. And furthermore, our paper is using two of these datasets. But you could use more or no datasets. And then there are other papers that are using other datasets. So this also creates like a network of the datasets that are used. And so it could be a kind of a complicated network. So when a new author appears, well, he's confused because he doesn't know what dataset to use. So that's the motivation. We want to build a recommender system for this new author, for this author. So when he looks for different mesh terms, then we can recommend him some of the datasets. So now a little bit of background. Well, all of this network can be represented as a sparse tensor. In the x-axis, we have the mesh terms that the author is looking for. In the y-axis, the datasets that were used for publishing the paper. And in the z-axis, the authors that used that wrote the paper. And so to build a recommender system, the question is, given an author and a mesh term, what is the best dataset that we can recommend? Or in other words, what is the probability of the dataset given both the author and the mesh term? And this, well, it's important to notice that these two are not independent. So we have to take that into consideration. And the way we did this was by building a Bayesian network. So building a Bayesian network takes into consideration the relation between the mesh terms and the authors. So the mesh terms is well, we have the probability distribution of the mesh terms, and there's a dependency with the authors, so that's a bivariate distribution. And then if we take these two into consideration, we can have the probability distribution of the database. So here in the bottom part, we have a table that says, so given an author and a mesh term, we can give a probability for a database. And well, all the probabilities in each row have to sum to 1. And now, what about a cold start? So if we have an author, can we still recommend some databases, even without the author looking for a mesh term. So given two authors, how are they similar to each other? So we built a Jacquard index. It's very similar to the Jacquard index. What it does is that it takes the publication that both of these authors had in the same journal, and also the mesh terms that were used in their respective publications, and then we just divide it over all of the different publications and the mesh terms that were used by the authors. And this gives us a similarity between two authors. So once we have a similarity, we can build like k-medias clustering. So here we have a representation of how the clusters work. So we have like in this case we have 3 clusters, so we can recommend some databases to each person in each of the clusters. So when a new author appears, we can just cluster her into one of the previous clusters. And so we can just recommend her whatever datasets were recommended in that cluster, without her even having to look for a mesh term. So that would be good for a gold start. And well, each author has a different probability distribution of belonging to each of the clusters. And so we can base our recommendations for a database just based on this k-medias clustering. We also have over 2,700 datasets, so we would like to have some way to use the dimensionality of it. So again, given 2 datasets, how are they similar to each other? And we built a Jacquard index, which is very similar to the previous one. Two databases are going to be similar based on the authors that have published using that dataset, and also based on the mesh terms that were used in the paper that was published using these datasets. So again, this gives us a similarity index for the datasets, and well, this is a hierarchical clustering of all the datasets. It's not very clear here, but if we make like a zoom here, we can see, well, the closer they are to each other, the more related the databases are. And well, we wanted to see also like how many clusters should we have. So there's the elbow method that says like just count wherever there's like a big difference. So there are like 3 big differences in this graph. And so based on this, we build the accuracy based on each of the amount of clusters. So we can see that the accuracy is beginning to drop, and then it starts growing up again. But in this case, in classifiers, it's also important to take into consideration not only the accuracy, but also precision and the true positive rate and sensitivity. So here's a graph and all the formulae for all the other ones. So it can be sometimes confusing. So in the second graph, we see that the false positive rate is declining constantly. And even though this one is declining, well, everything is kind of declining, but then in the end, the more clusters we have, the higher the precision and the higher the recall. Well, we also are examining another approach, which is given this tensor, we can do a kind of comparative tensor factorization. And the idea behind it is that we have the tensor that we showed at the beginning, and we try to factorize it into another tensor, so diagonal tensor, so it's a very simple tensor. And 3 matrices, U1, U2, and U3. And this can be generalized to any amount of dimensions. So this factorization is kind of like SVD, but there's no need for orthogonality. Orthogonality is nice, but it's not required in this case. And this allows more flexibility as opposed to the traditional user item matrix collaborative filtering, because we can add more dimensions to the tensor. Well, this is a work in progress, so we're on it. But so the idea behind this is that we have to find the U1, U2, U3, the lambda, and then R. So R is the rank of the tensor, such that we can factorize it in this way. It's just going to be a sum of outer products. So this R is a smaller rank than the original tensor. And well, even though our tensor is sparse, it's going to be factorized into dense matrices. And to get back our sparse matrix, we just have to do the outer product of these matrices. And so the recommendation for a specific point for ijk is just going to be adding a multiplication of subharmonics. And so this is very, very easy because this is a regular product. And so it's going to be very fast to do this. So training the model is tedious and it's going to be time consuming, but once we have it, then testing is going to be much more faster. Well, summary and future directions. So we built a recommender system for databases. Use the Bayesian network to consider the dependencies on the variables. A clustering algorithm is applied to improve the efficiency for a whole struct recommendation. Also, a hierarchical clustering is applied to the databases to reduce the dimensionality and improve the speed and the accuracy of the recommendations. And the tensor factorization will be further explored to make an efficient recommender system and reduce the dimensionality. Finally, I would like to thank my mentor, Dr. Xiaochen Jiang, collaborator Arya and Mer, who helped me with the databases and some ideas, to all the professors and staff and interns, iDASH and DBMI and NIH. Thank you.
We have time for one quick question. We don't have extra mic, so speak loud. Anyone? Okay, so let's start right now. Our next speaker is
Hello, everyone. I'm very glad to talk about my iDASH project. The topic is modeling pain data using restricted Boltzmann machine. My name is Lei Yang, and in this summer, I was mentored by Dr. Shuang Wang, and also co-mentored by Dr. Xiaochen Jiang and Dr. Hyuneng Kim. I'm from University of Oklahoma and majored in Department of Electrical and Computer Engineering. In this presentation, I will talk about the motivation, why we want to do the pain research, and we will see our data and what kind of a method we want to use. And we will also show some experimental results. This presentation will end with the discussion about future work. So pain is a very important topic. But in our project, we concerned about a special case. So in intensive care unit, some patients may in coma state, so they cannot tell their feeling. So we ask ourselves whether we can predict the pain state using recorded physiological data. If so, the doctor can take actions to free the pain of patients. There are two objectives in this project. The first one is we want to verify whether a model called restricted Boltzmann machine can be used to represent the pain data. But in the long-term future, we want to construct a deep network to explore the pain data. This is the data we used. Our data was collected from almost 7,000 patients. For example, in this flow sheet, the first and last column are patient ID and recorded time. Both of them were encoded to protect the patient privacy. The three middle columns are the feature names and feature value we used. Even though we have hundreds of thousands of features, we only selected 78 numerical features based on our previous research. So we made the first assumption that pain may have different pattern in different individuals. Therefore, we considered about individual data. For example, in this data matrix, we have 80 columns. The first 78 columns are corresponding features. The next is the pain state, and the last one is the time. It is important to note that in this data matrix, not every element is recorded. In other words, we have a sparse matrix. So in the following slides, maybe we are talking about a pure machine learning problem. In the beginning, we have three considerations about the data. First one is incomplete data. We already see in a previous slide. In current stage, we synchronize data. Simply put, we make interpolation about data. The next one is we don't have enough number of labels. So in current stage, we only perform experiments on the patients with a large number of labels. The last one is time information. In current stage, we ignore time information. So in a learning problem, the most important is the representation of data. In this project, we consider about a powerful model called restricted Boltzmann machine, or RBM. So RBM is simply a two-layer graphic model. So in the bottom layer is visible layer. For example, in our case, we can put 78 features into the visible neuron. And the introduction of hidden layer can increase the impression power of the model. And Boltzmann means the joint probability can be denoted by the Boltzmann distribution. So-called restricted means there's no connection between the hidden layer or visible layer. So simply put, given a training set, we want to learn the parameters. It is generated by maximum likelihood, and the general solution is gradient ascent. In RBM, we're using contrast divergence method to tackle the problem. And when we have the parameters, we can calculate the energy and the probability. We will show the discriminate RBM in the classification in a later slide. We also mentioned that since in this stage we use the standard binary RBM, therefore we also convert the numerical features into binary features. We simply feed the original feature into a Gaussian probability distribution. So right now the xi will denote the probability of a current value ti in the normal state. And in this slide we show how to do the classification test by discriminant RBM. The trick is we incorporate the pain label C into our feature X. Then we can learn the parameter of the for the feature V. So the classification is we want to calculate the conditional probability of label C given the feature X. Then since the probability X is fixed, then we can calculate the joint probability of V1 and V0 by the energy function. And we perform the experiment on 4 patients using 3 methods. First, we use the PC plus SBM. And we can tell in this experiment, we have like 28 non-pain states and 10 pain states. But the method of PC plus SBM found 8 false pain and 1 false non-pain. So we also use a linear discriminant analysis method. Even though the false pain decreased, but the total accuracy stayed the same. So the performance was not improved. Another experiment we use in RBM, we can tell we have only 4 false pain and 1 false non-pain. So the total accuracy was significantly increased. To show the performance, we also draw the RC curve and calculate the AUC value. For AUC value, the higher number means the better performance. So we can tell in the experiments of 1, 2, 4, 5 individual, the RBM achieved the highest performance. We also show other experiments on individual 6, 5, 6, 3. RBM also achieved the best performance. It also happened in individual 7137. RBM achieved highest AUC value, and also the 4822. So this is a table about performance comparison. So in all the experiments we conducted, most of the sensitivity and the specificity, the RBM achieved the highest performance. For all the AUC value and accuracy, RBM achieved the highest performance. So in summary, we think RBM can be used in modeling the individual pain data. Also, for the task of classification, we think RBM is a better model compared to the other leading models. So in the future, we consider about, because the better features are very limited, the higher value and lower value may have totally different meanings. So we prefer use of the max instead of banner. And we also show in our experiments, actually, we also performed some experiments using the first half data and classification in the second half data. And all of the methods achieve a poor performance. That means time information is very important. And the last one is, since deep network need a large number of data, so we will use the whole patient data as the training data. For the individual, we will use the individual data to fine-tune the parameter to avoid overfitting problem. That is our current stage performance. So I want to thank my mentor, Dr. Shuang, and co-mentor, Dr. Xiaoqian, and Dr. Henry King. I also want to thank all the professors and intern. Thank you.
So we have two questions. Okay, I have one question. So you mentioned that the data is short of label, but in your slide you said you are using the data with 1,000 label. It means 1,000 pain?
Yes, because we have almost 7,000 patients, but we choose the 4 patients. In these 4 patients, they have the recorded labels. The labels is pain or non-pain, but the total number is larger than 1,000.
Oh, okay.
So we have a large number of labels.
So this patient has been suffering enough. Maybe next time we should push towards the ones that have less pain.
Yes.
Okay, thanks. Okay, so our next group will be Nima and Suyash. So there's a group of
Good morning, everyone. In the beginning, let me thank you all for giving us the chance to present the summary of our work we contributed to in the last few weeks. My name is Dima Arif. I am a senior student in the New Jersey Institute of Technology, and this is my friend Suyash Rathi, a master's student from Syracuse University. The key points of our presentation will include an overview and motivation, data preparation, proposed services, secure comparison, and future work. And the title of our project is the Privacy-Preserving Similar Patient Query using secure multi-party computation. So the idea of our project is to establish a scientific and social web service that helps the publicity to find their rare mutation disease match and give them the chance to connect it through encrypted secure channels. Similar services exist, but it lacks the security and privacy of patients' data. Also, our service is unique because it does the match based on the genotype level, which gives more accuracy. Also, we give the patient a chance to connect it through securely channels to communicate and share their conditions, symptoms, treatments, and the journey of healing process, while their sensitive data remain private and secure. So in simple words, how does that work? A user can simply provide his genetic data in a VCF format to our server where it gets securely compared with our available profiles. The mismatching profiles in terms of phenotype will be displayed to the user, with the matching score along with the medical conditions. Also, we give the user a chance to see the medication that the other patients use. Also, we give the user the chance to pick the conditions he or she has, which help us improve the order and ranking of our medical conditions. I would say data preparation was the tough part of our project, and the data we collected as a starting seed of our project is obtained from Personal Genome Project, which I'm going to call PGP for the rest of my presentation. PGP provides a rich content data without any structure, which makes it hard for doing any query or research. PGP has over 4,360 public profiles, and it was challenging to mine and analyze this data. Most genetic data which was supposed to be in VCF format, were in various different formats, and some of them were unreliable. In cases we have patients uploading only their sequence files, not the VCF file. It took multiple steps of data crawling, mining, and analyzing to produce a consistent and structured database where we can do different queries and do the matching in an efficient way. So in the first step, we wrote a couple Python scripts and we ran it to download and crawl all the data from PGP. And in the second step, we did data mining and analyzing to give the data some structure and content at the same time. So as a result of the big mining we did, we were able to obtain about 1,000 medical conditions and 430 treatments in the database. And here is a histogram that shows the top 4 diseases we found that most profiles shares. And as a result, their treatments are the top 4 in the treatment database as well. Our proposed web services, in addition to what I mentioned earlier about using the genetic data to securely match patients and give them a chance to connect, the user will be given the chance to donate their genetic data. If they decided to do so, it will be securely added to our growing benchmark. Users will have the option to connect through encrypted channels to communicate and share their experience and support through the process of treatment or healing. Our service also included querying in the phenotype level based on the data we have available, which is not provided in any other services, like Patients Like Me and PubMed. Smartphone app is a way to be added to our project, which will make it easier to connect users and build discussion forums where multiple users can participate and share. And now I will pass the mic to my project co-worker, Suyash Rathi.
Hello everyone, I'm Suyash. So I come to my part of the project. It's basically security. So how do you actually ensure security for a user? Simple, you just don't save the data. So this is where we come to multi-party computation. So what multi-party computation does is you actually just compute whatever you need from the user data and you don't save the data. So, and how do you compute that? Using gates. So even the computation itself being secure. So here you can see that there is 3 inputs, A, B, and R, and some output is coming. So A and B are say 2 parties, their inputs. R is random numbers made basically the security part, and output is what we actually need for the computation part. So this is basically multi-party computation, and this is how we actually ensure security. And GMW is basically the protocol we'll be using. There's others, but GMW works best for our needs, so we're going ahead with that. So how would an actual framework, a traditional framework work? And what we have done to actually overcome their limitations. So if we have a database, say of VCF files, and we have a user query, the patient query, which we need to compare with the entire database of VCF files. So what a traditional framework will do is, every time each and every VCF file in the database has to be compared with the user query in a secure setting, and then get an output for each and every file. Now doing that for each and every file in the database I mean, and keeping the user query for that, I mean, doing so many computations, I mean, it's not that feasible. I mean, no, I don't think so. So what we do is we come up with our own framework. Since we have the database, it's on our side. We don't have to worry about security on our side. We can do whatever we want with the data. So we make a compressed table for comparison. We just compare the compressed table with the query VCF, and then we're done with the query VCF. That is the user VCF file, and then just the computation on that we have to deal with our files. So, I mean, that's basically the beauty of it. I think it will be better with an example, so I guess I'll just move on to that. So here you can see we have, say, database of NVCF files, and we have the MVC part, the GenW part, is the secure setting, where we're gonna be focusing on. So the database is compressed into the compressed table. Now that is actually the beauty of this part. I mean, that is the main focus here. So what we're gonna do is we're just gonna list which exact, I mean, ATGC, whichever of them is common in that position. For every position, we're gonna see which one is repeated. So say in the red box, it's G and E, which is being repeated. So just that is listed in the table, the compressed table. So that will be done for the entire N files, whatever as big our database is. And now why this would work? One would say that doing that for so many files, we just have all the values. No, but 99%, more than 99% for any chromosome, I mean, for any actually VCF file, it is similar. I mean, for one position. So that's why this would actually work for us, and otherwise it wouldn't have worked. So we compare this file, this compressed table, with our user input. We get a value, we just compare them, and we see which ones are similar. And now we compare that with each and every file, and we just have to simply traverse through them and add them, and we can directly get the value. So say in the first case, if we have in the first letter for the user input is A, and in our compressed table, just A exists. So the compressed table value would be 0, 1, 1, 1. Why 0? Because for another file having A, the distance would be 0. So we just need to add those distances for any other query in the database, and we'll just directly keep on traversing and we'll get our distance, how different it is from the user input. So that is actually how it works. So just one comparison with the user query, and we're done with the user query, and we just have to do everything on the server side. Now, these are some statistics that we've calculated. So I performed these on at the most till 8 database files, and it took I think a little more than 6 minutes. So this was just on a normal laptop. So, and this being independent files, we can do it simultaneously on different cores, different nodes. So the scale up would be 10 times for 10 nodes. And if we're working on cores, it would be multiplied the number of cores for those nodes. So this actually, I think, is feasible, actually practical. So this is how a performance estimate we have. So it is actually reducing by half every time we increase the number of nodes. And in case if we consider, I just consider a single core in the diagram. If you consider, say, 8 cores or 16 cores, like our servers would have, this would actually scale up to 160 times faster. That would be really nice and actually practical. So this is just the future direction summary. So this will be the first open source that will actually be there. I don't think a service of this actually exists. And so we basically match relation phenotypes, and security, the main part, is being maintained here. And smartphone app, as Ima mentioned, is one of the futures that we hoping to achieve. And we also encourage users to share data. So we can actually increase our database as we go. So it's, and really special thanks to Dr. Wang, Shao Chan, other professors, iDASH, DPMI, and NIH.
Actually, so you showed like the decreasing of time with increasing number of nodes, but the decreasing is stabilized after 8 nodes. What happens there?
No, it's actually reduced just half, so I mean it's very little.
Oh, okay,
But-
because the scale, right?
Yeah, I mean it's actually showing, it's not showing that, but if you magnify it, we actually just half it. So.
I see, I see.
And mostly because also this was performed on a single laptop. So there'll be certain, I mean on a server it will be better because your hard disk limitations, buffers and
Memory. Right?
yeah, exactly.
But in the end, you still need some communication costs if you're increasing number of nodes, do you?
Yes, so on a single laptop, I mean on like my laptop it would, yeah, but since we are dealing in servers, we have our own server, it won't be that much.
Okay, okay.
So in that case it will be really good.
Sure. Good job. Any other questions? Okay, so let's thank Divan and Suresh again. So next one is from Auditorium.
Good morning, everyone. Thanks for coming. Now I will make a short presentation of our project. As the title indicates, the topic is about the methods for the missing values of the distributed data. This project is supervised by Dr. Xiaqian Jiang. My name is Liu Wang. I'm a PhD student majoring in statistics from Oregon State University. Now let's start with our project problem. Here, we mainly focus on handling missing data. Missing data means that the data set we collected is not complete. That is to say, one or more variables have missing values. Missing data is a common complication in data analysis. In many medical settings, missing data can cause difficulties in estimation and making inference. So, it is often of interest to explore the ways to address this problem. In recent years, there's a large amount of literature talking about the statistical methods to dealing with missing data. And their work mainly focuses on handling centralized data. However, there is no more about the application of those methods to the distributed data. The reason why we concern more about the distributed data is that this is a usual setting in reality and trend of the biomedical research. On one hand, we want to get more data or collect more information to get a better or more accurate model. On the other hand, it is often restricted that we cannot share the raw data across the different sites to keep privacy. So based on those facts, the objective of our project is to apply the methods for dealing with missing data to the distributed data set. Then the methods. The simplest approach to dealing with missing data is to exclude individuals with the missing values. However, the estimate obtained from this complicated analysis may be biased if the excluded individuals are systematically different from those included. Inverse probability weighting is a commonly used method to reduce this bias. And in this method, the complete cases are weighted by the inverse of their probability of being a complete case. Besides inverse probability weighting, another leading approach is multiple imputation. This procedure replaces each missing value with a set of possible values that reflects uncertainty about the right value to impute. Then the imputed data sets are analyzed by using standard procedures, and the results are combined. Then for the distributed data, glory and vertical has been proposed for analysis on horizontally and vertically partitioned data, respectively. And this method integrates decomposable partial elements to allow us to build a shared model without transmitting individual level data. And the work we are doing here is making a combination of those methods to deal with the missing values without sharing data. Here is more detail about how inverse probability weighting works. Here we consider a linear model for regression of I on two predictors. The standard way to estimate the parameter is to solve the score equation, the equation 1, where the u theta is the first derivative with respect to theta of the log likelihood function. And for the data set shown in the red bottom, we have some missing y's that are indicated by the dot. To apply IPW, firstly, we create a missing variable r to denote whether y is observed or not. Then we fit a logistic regression of the indicator on the predictors and get the fitted probability of being observed. The weight, which is the inverse of the fitted probability, is given to each individual. And finally, we estimate the parameter by solving the adjusted score equation, the equation 2. We can say that in this IPW approach, only complete cases are included in our analysis, but weights are used to rebalance the size of the complete cases so that it is representative of the whole sample. To evaluate the performance of our method, we conduct simulation studies. In this section, we consider a linear regression model with two predictors. X1 is generated from standard normal distribution, and X2 follows uniform distribution. We set all coefficients to be 1, and the response is said to be missing based on the values of X1 and X2, so that the assumption of missing at random is satisfied. We choose the sample size as 1,000, and 1,000 replicates are generated. For each generated data, we split it into two parts horizontally and assume they come from different sides. Here we consider complete case analysis and inverse probability weighting methods. And glory is used in the process of IPW to build a shared model. Simulation results are summarized in this table, including the estimate and standard error of the parameters. We can see that both methods work very well, since the estimate of the coefficient are pretty close to the true value, which is 1. And also for the 1,000 replicates, we recorded the number of the 95% confidence interval containing the true parameter and got the percentage. It seems that the percentage is pretty close to 95%, which means that our t-test performs really good and is well calibrated. Additionally, another popular approach, multiple imputation, and more complicated cases where we have more than one variable have missing values are also considered. As shown in these two data sets, the dot indicates the position where there's a missing value. If there is a monotone missing pattern, as the left-hand table shows, the multiple imputation process for the univariate case can be repeated sequentially for the variables with the missing values. However, if there is no any missing pattern, the case will be more complicated, it will be more challenging, and more combination is needed. And this part of work is still in progress, and hopefully we can get some meaningful results. So that's about my project, and I would like to thank my mentor, Xiaoqian, for his great patience and for his patient guidance and great help. And many thanks to all professors, staff, and interns from iDASH and DBMI. I really enjoy working with you here. And also, I would like to thank NIH for your support. And thank you very much for coming and listening. Thank you.
Do we have questions? Okay, I said
Hello everyone. Today I'm going to present my project, SMART Rural, which is short for Secure Multi-Party Computation with Logistic Regression. My project mentors are Dr. Wang and Xiaochen Jiang. My name is Hao Yishi, a master student from Syracuse University, majoring in computer science. This is the outline of my presentation. Here we focus on horizontally distributed data. Suppose there are 3 hospitals, A, B, and C. Each of them has some private data. They may have the motivations to collaborate on the same research to increase the power of the study. However, due to the privacy concern, hospitals might not be able to exchange data with others. There are some existing work in this field, including Grower and Explorer, but they all have limitations. Previous work, Grower and Explorer projects can only protect patient-level privacy, where intermediary statistics and intermediary data are not protected. Spark uses the same keys among different parties. If the key is stolen, the adversaries are able to infer all parties' private data. For example, given the key, any party can decrypt intermediary statistics and intermediary data. However, in our SMART Rural project, we use multi-keys for different parties and are able to protect patient-level privacy and all intermediary information. In secure multi-party computation, functions are translated to garbled circuits. In this way, not only the user-level input are private, but all the intermediary information are also protected. Suppose there is a garbled circuit function f. It takes an input x from Alice and the other input y from Bob. During the calculation, neither of them could know the other person's private data nor the intermediary information. Logistic regression is one of the most influential models in biomedicine. It is a generalized linear model. It uses X and beta to support a binary decision. To learn the beta, we have to evaluate the maximum likelihood estimation. The maximum likelihood estimation is a concave function. To compute the beta, we often use Newton's method or Newton-Raphson algorithm. Suppose there are 2 hospitals, A and B. Their private data consists of X and Y. X represents patient records, while Y represents classification label. If we dig into Newton's method, we may find that the first and second derivatives are just combinations of local statistics from A and B. Previous work, Grower and Explorer, they may only protect patient-level privacy, while privacy risk exists in the computing procedure. In our project, not only the patient records, but all the intermediary information are protected. We provide a library of secure operations, including matrix addition, subtraction, multiplication, inversion, and exponential function. Our project is based on GMW, which is a secure multi-party computation framework. We made some extensions to GMW. GMW only supports integers, while in our project, we support real data arithmetics in pixel-point format. GMW only provides integer addition and multiplication. In our project, we provide a library of operations, including exponential function and matrix operations. GMW only supports circuits with fewer than 6 million gates, and we extend it to support up to 2 billion gates. Here we present some of the experimental results in our project. Matrix inversion may be a key step in our project. we use an iterative method to approximate the final result. In our experiment, we evaluate the inversion of 4x4 and 8x8 matrices. We found that as the number of iterations increase, the mean square error decreases for both matrices. The MSE can get under 10 to the power of -5. To prove the accuracy of our project, we evaluate the project with real data sets in up to 4-party scenarios. In our experiments, we use an Edinburgh data set and 3 genome data sets. Each record in the data set has 3 attributes and 1 classification label. We perform the comparison of models learned from SNAP raw and ordinary logistic regression based on 4 real data sets. We can see that our SNAP raw produced very close results to those produced by ordinary logistic regression. We also operated the same data in 2-party, 3-party, and 4-party scenarios. We can see that all these setups generated exactly the same outcomes. We also evaluated the performance of matrix addition, multiplication, and inversion. The bar plots show the communication cost, and the line plots show the computing time for the circuit under 2-party scenarios. We can see both the computing time and the communication cost increase significantly as the matrix size increased. This is because the circuit which implements the functions to be executed contains more gates when the size of matrix increase. I have finished the paper and submitted it to TBC Conference 2015. Here I will briefly introduce my second project, Secure Patient Linkage. Patients may receive services at multiple hospitals in a region. Integrating health records across the hospitals is critical to developing a more comprehensive and accurate picture of health and health delivery for the patients. Every node linked patient records across the institutes in Chicago. Their framework needs a trusted third-party server to perform the hash comparison. However, in our framework, we release the restriction by using secure multi-party computation. Right now, we are able to securely link patient records between 2 parties based on SMC. In this project, I used voter records from Ohio and generated 7 hashes for combinations of social security number, first name, last name, and date of birth for each record. Each hash has 512 bits. We could identify the simulated voters in 15 minutes when each party has 150 records. If we perform the secure patient linkage in iDASH cloud, which has over 800 cores, we would be able to link 100K by 100K records in 1 day. In this summer, I implemented a model for greater logistic regression based on secure multi-party computation. I also built a prototype for secure patient linkage in the summer. In the future, I will extend the fixed point SNAP raw project to floating point to increase the precision. I will also extend the 2-party patient linkage to multi-parties and parallel the computation. Again, my mentors are Dr. Xiaoqian and Zhi Shuang. Thank you for everyone who has supported me.
So, any questions? So,
so when you say 2 billion gates, how exactly do you handle the memory there? Because 2 billion gates is quite a lot. And say in some Garble circuit framework, you have a generated entire circuit, and that would be gigabytes of size of circuit, and you have to transfer it over. And how long does that take exactly when you run 2 billion gates with GMW protocol?
You mean 1 million gates? Or?
You say that you extend to 2 billion gates, right?
Yes.
And how much memory does that use exactly, and how long does it take? In a real life scenario, say you have 2 remote servers.
Okay. In our experiment, we have our circuit has like 106 million gates, and it takes like 2 hours to compute.
So if billions, it would take months.
No. That depends on your party members, because we found that OT occupies most of the time. That's why I told you if we can parallel the OT procedure, we can reduce the time.
Wait, but you cannot parallelize the network though, because network is mostly the bottleneck in CPU party machine. Even though
We have already found ways. Wait for my second paper.
Okay, let's talk offline. Okay, so we're going to take a group picture together outside. Hayan will help us align and get a picture together, the DBMI tradition. For the audience online, we will be back at 10 o'clock, and there will be a few other presentations remain. Thank you. So let's get outside. We'll take a picture in our new BIS building with the iDASH board.
Why don't you just go back? No.
okay, I have
So let's get back to our session 2. The next presenter will be Pallavi from University of California, Davis. Let's welcome her.
Good morning, everyone. Good morning, everyone. I'm Pallavi Rao. I'm going to be talking about the project that I've been working on for the past 2 months on unstructured clinical data extraction using NLP, or natural language processing. I'm a health informatics master student from University of California, Davis, and my mentors for the project are Shinan Su and Tim Ko. And there were 2 parts to our project, and one of them was to support the P-scanner cohort data element phenotyping with natural language processing for the 3 diseases that UCSD is part of for the P-scanner project, that is Kawasaki disease, obesity, and congestive heart failure. And the second part of what we worked on was medication synonym identification using RxNorm as a gold standard. What we tried to achieve was to extract cohort-specific data elements from the clinical notes. But we realized that although most of the clinical information is captured as structured data in the electronic health records, but there's still a gap in data extraction of unstructured clinical notes. And also there was very synonymy in the clinical notes. So we came up with 2 solutions. One was data extraction from the clinical notes using regular expression and natural language processing. And the second was identification of synonyms using RxNorm. This is the workflow that we followed through our project. We started with identifying the phenotypes for each of the cohort data elements, and they were annotated into the clinical notes to set a gold standard. And we tried to identify the same target phenotypes using NLP extraction, and the two were evaluated for results, and the results were then integrated into OMAP data model. I would be explaining this much more in detail using Kawasaki disease as an example. So for the Kawasaki disease, we used the publicly available notes from MD samples and I2B2, and then we screened these notes using the search criteria for Kawasaki, or fever and rash and child, as it's mostly seen in children. And we could narrow down to about 33 relevant clinical notes that we used in our project. We took the help of physicians to narrow down specific target phenotypes for each of the diseases, and they were then mapped into SNOMED CT concept maps. All the target phenotypes were then annotated into the 33 clinical notes using RAD annotation tools. This was how we created the gold standard for comparison. And then we created regular expressions to extract the same phenotypes for natural language processing. And as you can see, there were 2 types of data that we generated. One was from the predicted data from NLP, and then the annotated data from the gold standard. And the 2 data were compared and matched to find out, to generate our results in each case for each of the clinical notes. And this is a comparison of our results. We did the exact same process for obesity as well, and these are the results we obtained for both Kawasaki and obesity at the mention level and the note level. We used 33 notes for Kawasaki and 7 notes for obesity. And we're right now in the process of doing the same process for about 30 nodes for obesity as well. This is an example of some of the results we obtained for Kawasaki disease for mention-based extraction. And as you can see, even though most of them have high scores, some have low scores as well. And these would include laboratory tests like electrolytes, WBC counts, or urine analysis. These are the mention-based results we obtained for obesity. And even in this case, most of the low scores were for medications and laboratory because they were the ones that had the most varied synonyms that was used in the clinical notes. And this is what drove us to the second part of our project. We tried to identify the synonyms in medications in clinical notes. So we used the KD medication data that we had, and we tried to check for two things in those notes. One was for generic versus brand name drug mentions in these clinical notes, and medications that were not included in the RX1 terminology. So we used the target phenotypes from the KD medication list and generated generic names. And we used the same generic names to then find out the brand, existing brand names. And we used many different websites and databases to search. But primarily we used WebMD, Medscape, RxList, and drugs.com. We validated the quality of our search by comparing it with the terminology standard that is RxNorm. And we also, we tried to see the occurrence of both the generic and the brand name drugs with about 2,000 empty sample clinical notes. This was the result obtained when we evaluated our findings with RxNorm. And the higher recall here indicates that our results matched well with what was already present in RxNorm. And the low precision here indicates that we were successfully able to identify more medications than what was listed in RxNorm. And among all the medication listing that we had, we could successfully identify 100% recall for 53.8% of the medications. This is the result we obtained when we evaluated the occurrence of the generic versus brand names in 2,000 empty samples. This is just a sample of all the medication that was used. And as you can see, some of them have 100% generic name preference, whereas some like warfarin and enoxaparin are more preferred by the brand names, and among them about 23% of the brand names were not included in RxNorm, which proved a hypothesis that RxNorm is not as comprehensive when it comes to synonymy of brand names for each of the drug classes. Our future directions would be to continue the extraction process for congestive heart failure and also integration of the data into OMAP for all the 3 diseases, and expand the extraction to more concept-based instead of just the mention-based, and expand the synonymy expansion for all 3 diseases and also for RxNorm codes for obesity and CHF as well. And I would like to thank the principal investigator of the PScanner project, Lucilla Ono, and my mentors and DVM staff for this opportunity. Thank you.
Thank you. Any questions? So if no question, let's welcome the next presenters. There's teamwork from Donghan and Chao Jiang from University of Oklahoma.
So hello everyone. Today we will present trends in biomedical informatics, a study based on JML articles since 2009. Our project mentor are Dr. Shuang Wang and Xiaoqian Jiang. And my name is Donghan, a second year PhD candidate. And my teammate Chao Jiang, who is a master's student. We're both from University of Oklahoma. And And here is the outline of today's presentation. Biomedical informatics is a growing interdisciplinary field where research topics and citation trends evolve rapidly in recent years. It is important to better understand the relation between biomedical informatics topics and citation trends. Some previous studies have been done on examining the fact on articles such as the paper by Dr. Kim and John. But there are some limitations, such as they need to manually get data and assign 9 categories to these publications. In this study, we developed Python scripts to automatically clone data through Web of Science API. Following the previous study, we defined 9 main topics for all articles based on their match terms. We also used citation counts per month as CPM, which was first described by Dr. Kim in 2009. In this study, we introduced tensor factorization to get fine-grained topic analysis based on match terms. According to former publication, we conclude 9 most popular match categories shown in this pie chart. Each portion represents the total number of articles in this category. The actual number we analyzed is 941, exclude the paper published in 2015 because of the absence of match terms and some articles we count as other. As you can see, electronic health records, medical informatics, and natural language processing are the major part of the JMIA publications. And this chart shows the match frequency of 9 categories, and each bar represents the percentage of articles for 1 year in one specific category. We will do further analysis in this chart. So based on what we observed, we found the electronic health record has the increasing trend from 2009 to 2014. Besides, number of articles in methods and algorithms are also increasing dramatically within 2013 and 2014. Number of articles in medical informatics, information storage and retrieval, prevention and control has shown a decreasing trend since 2012. So then I would like Charles to give a brief introduction of tensor factorization implemented in our result.
Hello everyone, my name is Charles. I will present to you the tensor factorization and our experiment result based on tensor factorization. Tensor is an extension of matrix which can be more intuitively present more than 2 dimensions of data. Thus, we can analyze our data while considering more than 2 factories. Tensor factorization can be recorded as a generalization of the matrix singular value decomposition to tensors. Our goal is to get a 3-way tensor to examine the relationship among topics, application year, and paper citations. Based on tensor factorization, the first dimension of our tensor is the year, which is when the article was published on JMIA, and the second dimension is represent match terms. The third dimension is the citation count per month. In figure on the left-hand side denotes the original tensor that needs to be decomposed, where each cell in the tensor is the number of articles. The right-hand side shows some interaction tensors, thus a Bayes tensor. The Bayes tensor captures the common characterizations for entire data, whereas the interaction tensors can capture some interesting representation of the data. For instance, in our experiment, we examine which topic has more citations in which year based on these interaction tensors. So in the following slide, I will to provide some experiment. So paper 1 shows the result of decomposition of 11 times 12 times 9 tensor, where each paper belongs to one of the 9 topics. The first dimension is citation count per month. We evenly divided the range of the CPM into 11 beams in log domain. The second dimension is the year, whose unit is half year, and the length is 12 for 6 years. The last dimension is mesh terms. In order to be consistent with the previous trend paper published in 2013, we also use the most frequent mesh terms. Each blue and red columns comes from one interaction tensor. The slide shows 3 tensors. The first row is the year. We analyzed the text in blue are from the non-predefined categories. The numbers in red are the weight of each category in a 2 years window, where a more popularity category will be assigned a higher weight. So we can see that the electronic health record always leads the popularity. This is we plot the figure based on our data. It also shows that EHR had the most popularity since 2009. Also, we found that the weight of medical informatics course increased in years 2010 to 2011, and then slightly decreased in years 2013 to 2014. Again, we plot the number of articles published in journal each year for medical informatics to justify our result. At the same time, we found that algorithm and method comes up with higher weight after year 2010. By the way, when we process the data, we assign the meaning and artificial intelligence and algorithms. So in our next experiment, we will see this detailed information. So we also plot the trend of method and algorithm. All these trend matches to our previous result. Note, method got the highest number of articles in 2013. In our following experiment element, we can also capture this information. So you see this slide, we analyze the data based on CPM, and it shows that the result is a decomposition of 11 times 12 times 9 tensor added both CPM and yields. We sorted the tensor in descending lambda, where lambda is the weight of each interaction tensor. From the value of lambda, we know that the most paper CPM's value located between 0.11 and 1.01, and at the same time, most of them are related with the electronic health record. Also, we got that the paper published in 2013 are most related with the method, and I mentioned the last slide. On this table, we got that paper related with the natural language process and published in the second half of 2010 had the highest value of CPM, whose average citation per paper is around 28. Table 3 is the top 3 natural language process paper published in the second half year in 2010. So this table shows the result of a tensor relation with 11 times 12 times 1,470 tensor. Here each paper may have multiple mesh terms on which most detailed subtopics can be captured, such as obesity appears in 2009 and pharmaceutical preparation in 2010. And I mentioned about determining artificial intelligence, and algorithm also comes up recent years, which didn't show up in our former experiment. This is the best tensor. We can know that the electronic health record is the most frequent mesh term appears since 2009. So that's all the result of our tensor factorization. So our paper is in regulation. So in this study, we developed Python script to automatically retrieve Genial publication data On the left side, apply tensor activation, we are able to get more detailed information than before. And so in the future, we are able to consider more factories such as households, institutions into the tensor factorization. So here I need to thank all these people for offering us guidance, and thanks MHI for the funding. That's all, thanks.
So, if no question, let's welcome the next presenter, Cole Dokaman from University of Virginia.
Hello. All right. Hello, everyone. Today I'm presenting my project, Privacy Transmission Disagreement Test for Kawasaki disease, that I've been working on for about 2 months. A little bit about myself. I am Ko Dogmai, or Nanati Dogmai, my full name. I just graduated from the University of Virginia. I'll be joining Indiana University for the PhD program in computer science. My mentor for this project is Dr. Xuan Wang, and I'm also collaborating with Professor Xiu Xian, Dr. Xing Qing, and Professor Yan Huang at Indiana University. So the goal of the project is to test the hypothesis that unique genetic variants influence Kawasaki disease susceptibility using 3D tests. Our computation is quite unique from traditional way in the sense that this is privacy preserving, and I will talk about that in a minute. It needs to be, we need to support multi-party. In our case, 3 parties in 2 different regions. It needs to be able to handle large-scale data. In our case, 1 million SNPs. And it also needs to do so efficiently in a reasonable amount of time. And we also want to come up with a general framework for privacy preserving computation for any functions or any future research on a large scale. So why do we do this? In our setting, we have 2 different institutions in 3 different regions of the world, and each of which possess some small data size. And if we were to let each of them do tests individually on their server, we are going to miss the results because of the small data size. We get insignificant results. But what if we can aggregate the data so that we can get large data size, and then we can come up with some statistically significant results. So that we don't miss the statistically significant SNPs. That is our goal. Well, that seems simple enough. In the traditional way, we want to have a trusted third party so that all the institutions can pass their sensitive data to a trusted third party. Let the trusted third party do the computation, then split out the result. Well, but why can we do that? Because there's some restriction. In reality, there are legal issues prohibiting exporting data. And there are some privacy concerns as well as security concerns. And another important question is, who can we trust exactly? And how do we even define the notion of trust? One person we trust can be, other people might not trust the same person we trust, right? Well, we have the potential solution as Hagi and Suyash has talked about a little bit earlier. We can use secure multi-party computation so that we only share the shares of our data rather than sending the whole data. And only we can retrieve the result. Okay. Now, this is the notion of security. What does it mean for a protocol to be secure? We say that it's security, we say that it's secure if it simulates the third party, meaning that the computing party learns as much as if we have a third party, but we don't have a third party. So we simulate it. Or another word, each party only learns the computation function, its own inputs, the outputs, what can be inferred from the outputs, and nothing else. That's it. If it doesn't satisfy these properties, it's not secure. So any heuristic approach wouldn't work. But how secure is secure, okay? We talk about security. In secure multi-party relation, the level of security is called provable security, which means it is proven in theory to be secure. So any engineering hacks wouldn't work. And we can set different security parameters so that they have different of security. But well, if you set it right, it normally takes 1 million years to crack one ciphertext. So nobody's going to do that. It rarely takes shorter, but still take years and supercomputer to crack one ciphertext. So we can be sure that this is secure. Now let's talk about what we actually want to do. This is TDG test, and what we do here is we have trios: the mother, the father, and the affected child. We want, for one SNP, we want to collect, we want to measure the frequency of transmitted allele and non-transmitted alleles, and we want to construct this 2x2 table called one SNP. Then we want to compute the TDG score, which is just b minus c squared divided by b plus c. And then we look at this TDG score follows the chi-square distribution with 1 degree of freedom. So we can look at the PYs in the table and test it is smaller than the threshold, and we reject the hypothesis. For further detail, you can refer to Dr. Jikun Kim sitting there about how we do this and why we do this. This is the entire procedure with our institution in place. We have one institution in US, UK, and Singapore. We want to aggregate all the BC pairs, which is what we are interested in computing TDG test, right? We want to add all the B's together, C together. The problem is we have a little m here to denote the number of SNPs, but we have up to 1 million SNPs. So we want to aggregate data. Then we want to compute the TDG score of each of them and look up the PYs. Then we want to pick the top K SNPs with the highest TDG score or with the lowest PYs. Or in other words, we want to pick the top K most statistically significant. And if we get less than K of those, then we just report less than K. That's pretty simple. And the parties only learn their own input, only learn the entire procedure, which is what I just described. The parties get the top less than or equal to K SNPs, as well as learning the time lapse of the completion. Now we come to secure multi-party completion. There are some known generic protocols for secure multi-party completion. And what generic means is that if you can compile any functions into Boolean circuits, you can run it in generic, in any of these generic protocols. In the two-party case, you have the Yao-Skyler circuit. In multi-party, we have many more. And the most notable one is GMW, because it is the fastest one. Well, so what's the problem now? We have everything set up. We have the protocols. Well, the problem is scalability. We can compute on small data, but if we were to scale it up to 1 million SNPs, that is hard. So the problem is SMC right now is that only two-party computation is quite practical. But others are not. If you try to scale to 3 parties, it's about 100 times slower. So what we have to do is we have to optimize the circuit size in order to make it practical. Now let's do some experiment. So this is the two-party setting. I use the FlexSC, which utilizes the Garber circuit, and we only consider aggregating data from two institutions. And there are 2 different settings for this: the high-speed network setting and the low-speed network setting. And the reason I'm dividing these 2 into different categories that, well, ideally we want to have high-speed internet. We want to have high-speed network, right? But in reality, it's not possible. We have one server in California and one server in Singapore, for example. So we have to also measure how it performs in slow network. This is the result. There is quite a lot here, but what I want to highlight is for 1 million SNPs, you have about 20 billion gates. It takes around, for the fast network setting, it takes around 270 minutes. So that's pretty fast. But again, this is high-speed network. In the low-speed network setting, we can approximate that. It's going to take around 300 hours. So that's not very practical unless you have high-speed network or you do on a small number of SNPs. Now another experiment is 3-party setting. I'm using my own Rust framework, and the CHK 2012 GMW backend. We aggregate data from 3 servers. So in the high-speed network setting, we have 3 local virtual machines running in our server. And in the lowest speed setting, we have 2 different servers, one in California, one in Ireland, and one in Singapore, to simulate our real setting in the US, and UK, and Singapore. So we are able to run only up to 1,000 SNPs, and for high-speed network, it's pretty fast. It's about 1 minute, but in lower speed network, it takes about 2 hours. If we were to scale up, well, let's compare 2-party and 3-parties first. For 3 parties, it takes about 10 times as long as 2-party. With our requirement of 1 million SNPs, 3 parties, and slow network, it's going to take about 2.5 months nonstop. So this is the scalability problem over here. Now we want to solve the problem by optimizing the gates. This is what I come up with. I come up with the Rust framework, which can use dynamically sized integer and can optimize circuit size. It is small footprint, which means that it uses less memory. And using Rust, you can get memory safety and thread safety. As of now, it can handle circuit generation and GMW backend. Now for the future plans, we can design some algorithms that is able to cache the TEG scores. We can also explore some other offline SMC protocols such as BMR, but it requires more memory. We can use somewhat homebrew encryption, which requires even more memory, and it's not quite practical right now. Or we can design custom protocols, but that is what we have to figure out later. So the conclusion is, MPC is practical on a small scale. In our case, 1,000 SNPs. We need massive optimization, of course, and we should try some other MPC protocols that might make it slower, make it faster. Sorry. I would like to thank Dr. Sean Wang as my mentor and other collaborators, which are Dr. Xiaoxian Jiang, Dr. Jikun Kim, and Professor Yan Wang from Indiana University. Thank you.
Anyone has questions?
Michael, so you mentioned the number of gates. Do you show the number on the size of the memory?
Yeah, I did not mention the memory consumption, but in order to be able to run, you need at least 16 gigabytes.
So how much do you actually consume?
How much? That's not that's the part that's pretty hard to measure accurately. But yeah, I will make sure that in the future.
I have one more question. Your performance is based on single core, right? If you have multiple cores, then you can scale up the performance.
So the problem with multi-threading is that you can only multi-thread local computation, but in multi-party computation, the bottleneck is actually network. As you can see, slow network perform way worse than fast network. So if you can multi-thread offline, that's good, but that's not going to help a lot.
But you mentioned you have like 10,000 SNPs. The calculation for each SNPs can be done independent, right? Then you can have multiple servers at local side, and the other party has multiple servers on the other local side. Then we can establish multiple communication channels.
Yeah, but that means that you need to export data to different servers. What if that's not practical?
But for the local party, it's doable, right?
Sorry?
For example, if you have a party, a first party, you can have 3 servers, and the other party can have 3 servers. Then you can have 3 communication channel and 3 servers. Then you can perform those computation in a parallel way.
Yeah, that's true. But, well, it's also mean that you triples the bandwidth.
Yes.
I mean, well, if you make internet faster, you of course can do it faster. That is like logical, but within the limitation, you cannot do very well.
Thank you. Any more
questions?
So let's welcome the next presenter, Michelle Doe from Boston University.
Morning, everyone. I'm Michelle, and my topic for this summer internship with iDASH is personalization, deployment, and testing of the cancer genomic analysis workflow. And my project mentor for this summer internship is Dr. Hers Mendy, and I graduated from the Bioinformatics Master's Program from Boston University recently. So the motivation for us is to make the cancer or clinical analysis tool more affordable, because at this moment, a lot of the analysis tools have complex and diverse dependencies that it makes it hard for them to translate between the labs that develop them and to other research institutions or labs. And this makes the reproducibility of results and data very difficult, even if they're working on collaborative projects. And so the pipeline that we focus on is a genetic analysis tool that's comparing the tumor and normal data that's used in the oncogenomic lab. And so what we do is we want to make this pipeline more transferable. And why this pipeline is important is because the comparison between the tumor and normal DNA will help the researchers to discover or measure the genetic biomarker that can help the disease, help them to find disease susceptibility, prognosis of disease causes, and also better prediction of treatments. And even more, once we understand the tumor and normal gene region differences, it might help us to further identify new biological pathways to cancer. And so to make this pipeline portable, we're interested in using one of the existing applications that's called Docker. And so what this is doing is for this specific goal that we're interested in, it's to make the application delivery easier. And how they package the pipeline is using something that's called a Docker container, and that's formed by the Docker images. And I'll go into detail of these two in the later slides. And to start with, I would like to introduce you to the whole exome pipeline workflow that we're working with. And how this pipeline works is that it takes the normal DNA and the tumor DNA and compare the genetic differences between these two to see what is the what could possibly be the mutation. And it will output with two specific types of mutation. One is somatic, and the other one is the germline mutation. And the difference between these two is the germline mutations are mutations that are only seen. The germline mutation are the mutations that are seen in both cancer cell and normal cell, whereas somatics are the mutations that are only seen in cancer cell. And even more specific into these two data, they detect two different sizes of mutation regions. One, the smaller mutations region that's called SNPs, and the other is the larger regional differences that's called copy number variation. And to do that, this pipeline depends on several different software applications. So for example, it uses BWA, PCARD, GATK, or SEMtool to do the alignment between these two, to compare the difference and align these two DNAs with, and then it will calibrate it to remove the duplication in the region, and also to remove the error within the region differences. And later on, after this process, we will we apply several filters to make the result even more accurate. And to do that, we use that tool, FP filter or SNP effect. And after making the results more accurate, we'll apply them with bar scan and generate the actual variants and the copy number regions. And so these dependency softwares are very diverse from each other, in which PCARD, GATK, SEMtool, and bar scan uses Java. And FP filter is written in Perl, and some of the other application uses R or Python to be able to function. And on top of the software dependency, this workflow also depends on several resource data to make the process work. And so some of the database that we work includes dbSNP or the SNP effect dictionary. And to do the quality control, we rely on the variant count and the substitution profile or the overlap between the databases. And so with such a complicated workflow, we will need extensive preparation to install the software or to download data correctly to make it work. And so this is where Docker will come in handy. It will make the sharing process and also the packaging process much easier. And so what exactly is Docker? So Docker is formed by two main components. One is the Docker container, the other one is the Docker images that form the container. So what Docker container is create a virtual environment that is similar as the working pipeline. And then the Docker images will be all the dependencies that's used for the workflow to work, the pipeline to work. And so this concept is actually similar to one of the more traditional way of doing this kind of application called virtual machine. And the difference between virtual machine and Docker is that virtual machine will have a full operating system installed with the associated overhead of the virtual device driver and the memory management. Whereas Docker container will share the same operating system and the device driver as the host. And so both VM and Docker container will be able to ensure that same environment as the production stage where the pipeline was working. But then the virtual Docker container will have smaller, because of the characteristic of Docker, it will be smaller and should start up faster and have better performances. And so how Docker is making the sharing of the pipeline easier is that can be shown in this graph. And this is how a Docker container or a Docker image is actually laid out. So for example, the TM-pipe Docker image that I compiled looks like this. So I have a base layer of the Ubuntu Linux package. And on top of that, we'll install a few layers of the basic language, the supporting application, and the software on top of, and as well as the data resources or the TM-pipe script that you use to run this pipeline. And so this, so with this stack of image, Docker will be able to bundle up and create a Docker container that is packaging, that's creating a box that has all of the dependencies necessary for a working workflow. And so with this Docker container, it could be transferred onto any machine, any personal computer, or even iCloud, because it is not restricted to a specific infrastructure. And so for the TM-pipe Docker image, it's about 2.5 gigabytes large and has about 24 layers at this moment. The compile time is around 30 minutes, which is not ideal, and we're looking to optimize it in the next few weeks. And so the samples that we run to test this pipeline at this moment is a blood and a tumor exome sample from human. And the runtime when we do it on Docker containers is about 14,000 seconds, that's around 4 hours. And when we do it on the VM, it's about 12,000 seconds, which is about 3.5 hours. And so this container can still be optimized and improved in the future. And so that's one thing that we will be working on for the next few weeks. And to summarize my project, the Docker TM-pipe contains all the dependencies, including all the software or the resource data and script that's important to run the pipeline. And this increased the portability and made this Dockerized TM-pipe easier to be shared within machines, among machines. And this increased the research reproducibility because of the easy share characteristic, and also because it will produce the same working environment as for all of the research teams that are using it. And so for our future direction, on top of optimizing the Docker image that we have, we are wishing to see if we can replace some of the license dependencies that are currently used for the pipeline, for example, GAPK. Because at this moment, we will not be able to actually push onto the public Docker hub, as we'll wish to share it even more. And after we finalize the Docker image for TM-pipe, we would like to compare the performance between different setups. For example, on the Amazon Cloud or the iDASH private cloud, and also on FlyDeck, which is one of the self-service portal that we are developing at UCSD for optimization of VM's analysis workflow. And so to end my presentation, I would like to give special thanks to my mentor, Dr. Herz Mendy, my collaborator, Jihu Kim, and Tyler Beth. I would also like to thank all the professors, staff, and interns on iDASH, DBMI, and NIH.
Any questions? So, if no questions, let's welcome the next presenter, Rodrigo Gam from Federal University of Parma in Brazil.
Good morning, everyone. My topic for this summer project was IC, Intelligent Search Extension. My name is Rodrigo Leão Batista. I'm a third year undergraduate at Federal University of Paraná, Brazil. I studied for 2 semesters at Arizona State University as an international student of the Brazilian Scientific Mobility Program. The project I worked on this summer was IC, Intelligent Search Extension, and I was redesigning and recreating the user interface for the system. My main goal for this project was Unity. Before I start to talk about the project itself, here's a little background information. Nowadays, a large amount of biomedical data are available due to the fact that technology has been helping us to process information faster. So we can use this information and create new hypotheses and theories for our studies so that we can advance our understanding of human health and disease. But also it brings some challenges, such as addressing data quality. Even if we find and analyze data quickly, the value of the data will be jeopardized if it's not well accurate. But also, displaying meaningful results could be a problem. Even if we have 100% accurate data, if we don't know how to show to the user in a proper way, it would be basically useless. And in addition, there are some lack of accurate tools and poor data accessibility. So in order to solve some of these problems, there is an initiative project called BioCaddy, which is biomedical and healthcare data discovery and indexing ecosystem that facilitates the discovery and indexing of biomedical data in support to the large scale data analysis and reels. But okay, what is the IC? It is a pilot project funded by the BioCaddy initiative, and the system is sort of a recommendation system. IC uses existing metadata from DBGAT studies to support searching on large databases with sophistication and accuracy. It also efficiently reviews and filters the large amount of data returned. So this was the first UI version, the one I used as basis. It was a prototype and looks like a prototype for an old system, so I had to improve the interface. And then I started working on it. This was the first big change made on the system, always targeting clearness, intuitiveness, and easiness. We were looking for a more user-friendly UI, better look and feel, and also we included a sidebar menu that the user can hide and show whenever he needs it. And also we started to implement data visualization for our studies. The next UI changes are mostly related to a better usability of the sidebar it was created also a select studies section where the users can see all the metadata by clicking on a specific node on the graphical representation. Also, the visualization had some color changes to look more similar to the system, and we changed the visualization to show only the primary connections of the root study, because they are more relevant for the user. However, this visualization wasn't good enough. So we changed it again. Now, every node has the full study title, since words makes more sense than number or code for us. Also, by clicking on any node, a legend is added at the upper right corner with more metadata information fields. And also, this study is related to the node that you pick. But this visualization is still not good because we don't know which study is more similar to the root. We don't know if the old one or the one, because they have different colors and it means nothing, and the distance always is the same. Then, in order to improve that issue, we implemented color shading in distances to demonstrate the similarity among the studies. Therefore, the closer they are, more similar. We also used a tooltip when you mouse over any node with more relevant metadata information, and also it's easier and faster. And we also included the root study information featured on the left side, so it's easier and faster to compare information side by side. And also, in addition to, we made some visual changes on the sidebar, and now it's easier and clearer to see, and it's more intuitive. We also implemented table visualization. Table visualization is simple, it's easy, it's also a traditional type of visualization. We decided to include table because studies universe is really small. It's about 350 studies. And after this entire summer working on the user interface, we believe that this UI is the closest one to a great user experience. Now, one question that might come up is, how does the system work? Well, first, in a previous search page, the user does the initial search, which is going to search on MySQL database, whatever the user is looking for. And the initial return is going to have all the relevant studies related to the user search. Then the user finds what he's looking for, and he may think, well, I'd like to see more studies related, like this particular one. Then he can invoke the IC system by clicking on IC button. The default search will be used to calculate all the similarity scores among the studies related to the root. Once this calculation is done, a graph representation will be displayed. An optional step is to refine the initial search. Let's say the user wants to set some parameters and waits for recalculating the similarity, or even set a greater or lower similarity cutoff. It will be possible to search in that way, so the aspect that the user might think is more relevant, you can set and don't use the others. So this project is still going on, and it's planned to be done by the end of the next week, when it will be extensively tested. And after that, usability and generalizability tests will be performed too. And in addition, it's planned to write an abstract for email and a paper. So I would like to say a big thank you to my mentor, King, for all the support, the collaborators. EMD presented the first UI version of IC. Gina Wu and Claudio Farkas who gave me the right direction to follow in terms of visualization. All professors, staff, and interns of iDASH and DBMI and NIH. It was an incredible learning experience. Thank you.
Any questions? If no question, let's welcome the last presenter, Yang from UCSD.
Hello, I'm going to present my summer project, this project here in DBMI. It's called Dynamic. And data on physical activity, neural network assisted modeling, identification, and classification. And let's start. So my mentor is Dr. Kim, and also we work on this project. And in summary, our aim of this project is to classify data coming from various sources. There was a lot of projects, and for example, in DBMI we had the Francisco project, but there was some issues with classifying the data from activity sources. DBMI was busy classifying activity into several categories, and this project aims to strengthen these weaknesses and classify activity-related data into several categories. Activity-related data is going to be very, very useful in the future, especially in precise medicine. That's why we hope that this research will help to facilitate medicine in the future. So, formally, we had 2,400 labeled data points coming from various sources. Some of them comes from Francisco, some of them comes from DBGAP data and other NIH sources. Our task to classify it into 4 labels, into 4 classes. We had 3 activity-related classes called functional, status, environment, and activity level. And other thing is other, obviously. And the thing is, these labels are very, very specific and tricky to classify, even to annotators. So, for example, if you have functional status means your how does activity, how does physical exercise affect your health, affects your functional status of your body, for example, heart rate or the pulse, something like that. Activity level means how often you exercise, and activity level and environment are often tricky. Environment means physical barriers or facilitators that helps you to exercise or not, or prevents you from exercising, and other medical texts of medical information will be classified into other class. So initially we built very simple baseline. We had the normalization part, like some stemming, removing punctuation, normalization, and then we feed it into the dimensional reduction techniques. So combining this bag of words achieved with the dimensional reduction will get the LSA, latent semantic allocation. And then we applied some classification algorithms like gradient boosting machine or support vector machine or just tagging algorithms, and then get the prediction. So initially, this kind of approach gave us about 84% accuracy, but the problem was, if you look at the first line, we have standard deviation of 4%, and this kind of standard deviation is not reliable in the industry, in the reality. So when you have the real data, it will be very problematic to apply this kind of algorithms, and we need to apply something better. So better baseline would be usually in NLP we had only one type of features, like label for the TA by TA for whole documents. But in later years, NLP community come up with very, very powerful model called word-to-vec. And word-to-vec gives us better representation of words. We just project words from high-dimensional semantic space into low-dimensional vector space. And this kind of mapping gives us a lot of information, a lot of structural information. For example, vectoral representation of word man and woman will have the same distance as vector representation of word uncle and aunt. and the same distance as king and queen. Moreover, this word also captures plurality. Similarity, for example, distance between kings and queen will be the same as queens and queen. So we have a lot of more richer features just for free, just for using this kind of advanced model. This model is called Word2Vec. It comes from Google. We use the pre-trained model from Google because, like, as much data you have for pre-training, it will increase the accuracy overall. So currently, do you remember the previous baseline? So here, like, our pipeline changes. So we use Word2Vec for each word, get the list of words, and then just average it and get classification of it on this average representation of whole sentence, and then get the prediction. So applying this Word2Vec model gives us 2%, 1 to 2% improvement just for free, just changing the model and just averaging the words. However, some problems here is that we just average all the vectors and it doesn't capture order. But sometimes and often, order means a lot, especially in semantics. So, for example, if you have two sentences, I had my car cleaned, and another sentence, I had cleaned my car, they are semantically very different. But our previous algorithm just averaged everything to one-dimensional, into dimensional vectors that will be average of all words. So it won't capture any order. So we need to incorporate somehow order. Usually solutions in such kind of cases we need some dynamic time system, and for this purpose we use recurrent neural networks. So our pipeline would be like we apply Word2Vec, we get some representation of words, and just feed in time by word into RNN, and then get a representation and run another RNN. Like our RNN will be very complex. First part will be RNN, second part will be neural networks, and then we get the prediction. So RNN, like neural network is some kind of computational structure. We linearly apply something and then apply nonlinearity. And RNN is a little bit complex. We have also time dimension. So each time, like we feed word by word into this kind of model at the left and get the output at the top. And on this top, we will run neural networks and get the output. However, we also did some alterations. We added the LSTM, long short-term memory networks from the latest research. It's all the state-of-the-art research with inside the NLP is done with LSTM networks. So they had very good properties for us, especially they don't have vanishing gradients, they have blowing up gradient, but it's another issue. So our architecture was, we have been using the first layer had 300 units from the Word2Vec model. Then we feed it into the LSTM model that has 40 units. And like first part is 300 by 40 units was about time varying thing. So we feed all the sentence, like all the words from sentence into this first part, then get 40-dimensional output. And on this 40-dimensional output, we run 2-layer network, 40 by 40 layers network, and then output it to 4 classes that we had initially. And also we did bidirectional LSTM, so we can feed words into 2 orders. Like in forward order, for example, if I say I love you, we can feed I and love and you, but we also can feed it for backward direction, like you and love and I. Like this kind of information helps also to get better predictions because like words at the end won't be forget. Words at the beginning or words at the end won't be forgotten by the network because like we kind of averaging them. And so this kind of approach, like bidirectional LSTM or RNN LSTMs, like they get us 88 and 89% accuracy respectively. It's about 5% improvement of the initial baseline. And moreover, if you look at the standard deviation, our standard deviation also lower. So that means that on the real data, like on the real world data, we'll get more accurate predictions, more predictable predictions. And one other table of comparison. So initially our bug of words and TF-IDF methods, they get us very high precision, but very low recall. So overall F1 score was about 0.5, 0.6. So when our latest models, they give us about the mediocre precision, but also mediocre good recall, and overall F1 score increased in every class. So that means that this kind of algorithm will be better suitable for real-world predictions and also increase overall accuracy. That's why we think that's more appropriate to use this kind of models. And here's another visualization of our work. It's a very big confusion matrix is the latest model, and like on the right corner is previous initial confusion matrix. As you can see on the big confusion matrix, we clearly see the main diagonal, which means that our algorithm tends to predict right cases a lot, while the previous confusion matrix is kind of mixed. Sometimes we mix classes. And one other thing, what very good observation is most of our algorithms is able to distinguish non-activity data from the activity data. So activity data is the right corner, orange box. So everything besides the orange box is the blue. That means that we don't mix it up with other stuff. But everything else, like activity-related data, is kind of a little bit tricky. And when we analyze the output of this network, we figure out that sometimes neural network prediction makes sense, and our high-level annotated data wasn't precisely correct, so it makes sense for us. And our future plans is to, as I told, we pre-trained our model on the Google News. We use Google News data, Google pre-trained model. We are thinking about pre-training it on medical text because it might help also. And also we might think about training it on training with new techniques, kind of batch normalization or something. Also making the application. And that's all. Thank you for my collaboration to my mentor, especially with annotators Jimmy and Janet. Without data, we won't be able to get this awesome dataset. And to TVMI and iDASH and NIH. Thank you.
Any questions?
So I have a question. Your one-to-back model has a parameter k, right?
Right.
Which means how long the name.
Right.
Have you checked the impact of
No, I think Google's pre-trained model is k equals to 8 or 7. At the left you see 7 words and at the right you see 7 words. So it's very good window because it really depends on the data set. The data size, and Google has very big data set, 300 million of news.
I know, so that's what you're saying, that if we have medical pertaining data, then what might work better. So I was thinking maybe changing this case from the general corpus, the training may have an impact on our data and output.
Yeah, probably, but the main consideration is about the terms, because in Google Word today, they don't really, network hasn't seen the medical terms, a lot of blood pressure. No one talks about the blood or medical related fields in the news. But on the medical data, it will be a lot.
Right.
That's all.
Yeah.
Thank you.
Thank you.
So we had the pleasure to do a closing remark. Thanks all for staying with us for this productive 10 weeks. Some of you have only been here 8 weeks. I'm a true believer that productivity is positively associated with enthusiasm and curiosity. And this is evidenced by our cohort this year. So beyond not only the activity we organized, which is a kayak tour and movie night and also game night, this group is very active. You guys organize a whole lot of activities. So I know people have been going to potato trips, rock climbing, skydiving. Yeah, so I really enjoy it and see you all here. And I think you played hard and worked really hard. And so when you go back, for the ones who are leaving very soon, I wish you a safe trip. And also bring words back to your friends and welcome to apply in your next year. And for the ones who remain here too for the next 2 or 3 weeks, I hope you enjoy and the last few weeks for staying here. with us. And I hope everybody will end up with a milestone publication with one of our faculty members here. And so again, I will hand over to the workshop co-organizer, Dr. Shuang Wang, to put a final closing remark.
Hello everyone, welcome to the internship in the iDASH, and hopefully you have enjoyed your study here and enjoy our social events. And finally, we would like to acknowledge those project collaborators and funding agencies from NIH, and also the acknowledgement goes to all the interns, mentors, staffs in the division, and also the funding agency, NIH. Thank you very much.
Just a note, we have the lunch hosted at the second floor on the BRF, including the entire patio. So don't forget to go there at 11:30. So we will have the party there. See you.